Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, presents the conference. GPT, Generative Pre-trained Transformer. Most people, including many scientists and experts in artificial intelligence, think that it is limited to generative pre-trained transformers models. In this way, this vision of AI has become popular. HI considers that today artificial intelligence is generative pre-trained transformers and mathematical programming. This is the main theme of HI's research. GPT drives cognitive synthesis and the trend toward homogenization that occurs when using large-scale language models. GPT Artificial Intelligence. Alan Turing, a brilliant British mathematician and one of the leading scientific geniuses of the 20th century, is considered the father of modern computing and artificial intelligence. In October 1950, Alan Turing proposed a test. Was it possible to have a conversation with a machine and not be able to distinguish it from a human? He called this the imitation game. It was introduced in the article Computing Machinery and Intelligence. The intention was to use this test as a substitute for the deeper, more vague question, can a machine think? 70 years later, in 2020, several large language models such as OpenAI's ChatGPT passed modern and rigorous variants of this test. In 2022, OpenAI launched ChatGPT publicly and immediately captured global attention. It was the first chatbot you could have an extended conversation with on almost any topic, the first obvious application of a Turing test breaker. In 1950, many scientists thought this didn't make sense. AI's technological innovation is to create original content from vast data sets. However, it raises significant ethical concerns when it comes to bias and fairness. The quality of results depends on unbiased training data. Any internal bias can perpetuate discrimination. Biased data can lead AI models to reinforce stereotypes or overlook marginalized groups. Addressing these challenges requires transparency and rigorous evaluation of AI models and their data sources. Improving transparency and implementing robust testing frameworks is critical to identifying and mitigating biases, which fosters trust and ensures that they contribute positively to society, guided by ethical principles that prioritize equity and inclusion in innovation. AI has transformative potential for industries and social well-being, but it faces critical hurdles, such as data bias, algorithmic failures, and user interactions. AI bias produces unfair outcomes, as seen in biased algorithms for criminal justice, and in health AI that affect marginalized groups. Addressing this problem requires diverse data and bias-aware algorithms. By adopting these strategies, developers promote inclusive innovation, maintain ethical standards, and benefit communities universally. Artificial General Intelligence, AGI, is a theoretical stage of artificial intelligence, in which a software system possesses cognitive capabilities identical to, or superior, to those of a human being. Unlike today's narrow AI, which masters specific tasks such as playing chess or processing text, AGI could flexibly learn, reason, and apply knowledge in any domain. The key features of AGI are generalization, ability to transfer acquired knowledge from one field to a totally new one. Common sense, the ability to understand social norms and reason in a similar way to the human brain. Autonomous self-learning, ability to solve complex problems and acquire new skills without the need for prior human training. The fundamental differences of the artificial intelligences are AI, standard, designed and programmed exclusively to execute very specific tasks, such as machine translators or voice assistants. AGI, near future, you will understand the world as broadly as a person, adapting to any operating environment. A C, superintelligence, an even more advanced stage that would completely surpass the intellectual capacity of all humanity together. ChatGPT, produced by OpenAI, is the state-of-the-art commercial artificial intelligence GPT. Is ChatGPT a neural network? Yes, it is. ChatGPT is a natural language processing model that uses a neural network to power its understanding and conversational responses to users' text prompts. Specifically, ChatGPT works with a large language model, LLM, called GPT-3, developed by OpenAI and which has 175,000 million parameters. This is due to the current computational power and the great availability of data on the web. ChatGPT uses a feed-forward neural network as well as a normalization layer to generate its human-like responses. The feed-forward neural network applies a nonlinear transformation to the input stream, ensuring that the model can learn complex patterns in each dataset. The normalization layer stabilizes this training process by making sure that the input values have a relative scale size. It uses a machine learning technique, called fine-tuning, to ensure it responds to prompts accurately. However, it should be noted that, like any predictive method, it meets certain basic characteristics. You can set the accuracy of what you predict for the sample. In a regression process, this precision is called R-squared. As the number of parameters increases, the accuracy increases. But too many parameters lead to problems of overestimation. Accuracy depends on the quality of the sample, it can never explain what is not in the sample. Generative Pre-trained Transformers, GPT, are a family of neural network models that uses the transformer architecture and is a key advancement in artificial intelligence, powering generative AI applications such as ChatGPT. GPT models give applications the ability to create human-like text and content, images, music, and more, and answer questions conversationally. Organizations across industries are using GPT models and generative AI for conda, text digesting, content generation, and search bots. At the level of common knowledge, according to Generative Pre-trained Transformer, GPT, the current view of artificial intelligence, AI, is understood as GPT. Text extracted and adapted from a web search engine, based on GPT. Today, the public understands AI as computer systems capable of performing tasks that previously required human intelligence, such as conversing, creating images, resolving doubts or automating jobs. Summarizing the brain behind the applications too. Conversational assistants, tools such as ChatGPT, Claude or Copilot that answer questions and write texts. Content generators, applications that create images, videos, or music from a simple written description. Smart search engines, systems that not only provide links, but also directly summarize the requested information. GPT is much more than what is described, but it is far from being the only form of AI. A generative pre-trained transformer, GPT, is a type of large language model, LLM, that uses a specific neural network architecture to understand and generate human-like text. The theory behind GPT is built on three core pillars. Generative. The generative aspect refers to the model's primary goal, creating new content rather than just classifying existing data. Autoregressive prediction. GPT operates by predicting the next most probable word, or token, in a sequence based on all preceding words. Sequential generation. Once a token is predicted, it is added back to the input, and the process repeats until a complete response is formed or an end token is reached. 2. Pre-trained. The learning process. Before a GPT model can follow specific instructions, it undergoes a massive phase of unsupervised learning. Massive datasets. The model is fed billions of pages from the internet, books, and articles. Self-supervised learning. It learns the statistical structure of language, grammar, facts, reasoning, by trying to predict the next word in these texts without human-labeled help. Fine-tuning. After pre-training, models are often refined using reinforcement learning from human feedback, RLHF, to align their responses with human values and safety. 3. Transformer. The architecture. The transformer is the underlying deep learning engine, introduced in the 2017 Google paper Attention is All You Need. Self-attention mechanism. This is the brain of the model. It allows the GPT to attend to different parts of a sentence simultaneously to understand context. Decoder-only design. Unlike some transformers that use both encoders and decoders, GPT specifically uses a stack of decoder blocks optimized for generating text one step at a time. Parallel processing. This architecture allows the model to process large amounts of data in parallel, rather than one word at a time, making training much faster. The first person to predict and generate texts using mathematical models was the Russian mathematician Andrei Markov. In 1913, Markov published a pioneering study, where he applied Markov chains to analyze the first 20,000 characters of the verse novel Eugene Onegin by Alexander Pushkin. Key aspects of his work: pattern analysis, manually counted the frequencies of vowels and consonants, to show that the appearance of a letter depended on the previous letter. Statistical prediction, it established that, based only on the current state, one letter, the probability of the next state, the next letter could be calculated without the need to know all the previous history. Markov property, Markov introduced the idea that the future is independent of the past, given the present, a fundamental basis for today's natural language processing. Markov not only resolved a mathematical dispute over the law of large numbers and dependent events but laid the groundwork for modern technologies like large LLM and GPT language models. The text presents the summary of the life of the Russian scientist Andrei Andreevich Markov. His best-known contribution is theoretical work in the field of stochastic processes known as Markov chains, which today are considered an essential tool in disciplines such as economics, engineering, operations research, and many others. In probability theory and statistics, a Markov process is a time-dependent random phenomenon for which a specific property is fulfilled. The Markov property, or without memory, is one for which the conditional probability about the present, future, and past state of the system is independent. The most practical importance is the use of the assumption that the Markov property is valid to construct a stochastic model for this process. It is a simple way to introduce statistical dependence, in such a way that it allows the strength of the dependence of the different delays to decrease as the delay increases. The term Markov chain is often used to imply that a Markov process has a discrete state space, infinite or countable. Normally, a Markov string would be defined for a discrete set of periods, such as a discrete time Markov chain, although some authors use the same terminology where time can take continuous values. We can talk about different definitions about the first-order Markov processes. States, the conditions in which an entity or possible events are found. Trials, repeated occurrences of an event being studied. Transition probability, the probability of moving from state I to state J in a transition or period. Markov, first-order, processes, to be used as models of physical or economic processes, must have a series of characteristics. The probability complies with the Markov principle. Existence of a finite number of states. The probability must be constant with respect to time or period. The trials must be in equal periods. Markov decision process. Today, in artificial intelligence, it is the mathematical framework that underpins reinforcement learning, RL, that models an agent's sequential decision-making in a stochastic environment to maximize accrued rewards. According to Markov property, the future state depends only on the current state and action, not on the whole story. RL algorithms find an optimal policy, what to do in each state by learning from the states, actions, and rewards. The MDP is well understood when the state and the spaces for action are small. Bertzka's, 2007, and dynamic programming, PD, algorithms, such as value iteration, Bellman, 1957, and policy iteration, Howard, 1960, are standard techniques for calculating optimal policies. In large state space problems, exact DP is not feasible since computational complexity scales quadratically with the number of states. The development of GPT has been an extensive process in which many people have participated and many technical terms coexist. The first two topics are natural language processing, and LLM, large language model. From these concepts, the problems of estimation of artificial intelligence with deep learning are developed. Natural language processing, NLP, is a branch of artificial intelligence that allows computers to understand, interpret, and generate human language, either in written or spoken form. It's the engine behind tools we use every day, such as machine translators, voice assistants, Siri, Alexa, and chatbots. NLP is traditionally divided into two fundamental areas. Natural language understanding, NLU, focuses on analyzing the meaning, intent, and sentiment behind sentences. Natural Language Generation, NLG, it is responsible for producing coherent text or responses that sound natural to a human. There are three main approaches to developing these capacities. Symbolic or rule-based, uses rigid grammar rules programmed by hand. It is useful for very specific tasks but does not scale well in the face of the complexity of real language. Statistical, relies on probabilities and patterns found in large volumes of text to predict the next word or rank content. Neural networks and deep learning, it is the current standard, using architectures such as transformers, the basis of GPT, to learn complex contexts and deep semantic relationships. For a machine to understand a text, it usually follows a process, pipeline, that includes tokenization, dividing text into smaller units such as words or pieces of words. Stemming and stemming, reduce words to their root, e.g., running to simplify the analysis. Grammatical tagging, pause tagging, identify whether a word is a noun, verb or adjective according to its context. Sentiment analysis, determine whether the tone of a message is positive, negative, or neutral. Named entity recognition, NER, identify names of people, places, or companies in a text. At its core, NLP seeks to bridge the gap between human communication and computer understanding, allowing machines to interpret, analyze, and generate human language in a natural and intuitive way. NLP combines the advantages of computational linguistics, machine learning, and deep learning to process and understand large amounts of linguistic data. By leveraging these advanced technologies, NLP enables computers to understand the nuances, context, and intent of human language, whether spoken or written. This capability is essential for a wide range of applications, from virtual assistants and chatbots to language translation and sentiment analysis. The main goal of natural language processing, NLP, is to create systems that interact seamlessly with people, making technology more accessible and responsive to our everyday communication needs. As NLP evolves, it transforms the way we interact with machines, opening new possibilities for efficient, effective, and humane communication. Some of the main challenges of NLP are spelling mistakes, language differences, innate biases, words with multiple meanings, uncertainty and false positives, and training data. Natural language processing, NLP, has a variety of meanings depending on the context, sarcasm, metaphors, humor, or any underlying emotion it conveys. Understanding this phrase is natural for humans, however, machines cannot distinguish between different emotions and feelings. Various NLP tasks come into play here to simplify complications in human communications and make data more digestible, actionable, and understandable for machines. Some tasks include speech recognition, voice tagging, disambiguation of the meaning of the word, recognition of named entities, co-reference resolution, and natural language generation. A large language model, LLM, is a type of artificial intelligence. LLM is an advanced artificial intelligence systems designed to process, understand, and generate human-like text by analyzing patterns in massive datasets. Built on neural network architectures, primarily the transformer model, they use billions or even trillions of parameters to capture the complex nuances of language. Transformer architecture. Most LLMs use a transformer model. This model allows LLMs to process entire text sequences at once. Next word prediction. LLMs predict the most likely next word in a sequence. This is based on patterns learned during training. Parallel processing. LLMs use GPUs to train in parallel, which speeds up the process. How they work. Transformer architecture, introduced in 2017, this architecture allows models to process entire sequences of text in parallel rather than word by word, making training highly efficient. Self-attention mechanism, this is the brain of the transformer. It calculates how much attention to pay to every other word in a sentence to understand context, such as distinguishing if bark refers to a dog or a tree. Tokenization. LLMs break down text into smaller units called tokens, words or parts of words, which are then converted into numerical vectors that the computer can process. Training phases. Pre-training. The model learns general language patterns by predicting the next word in vast amounts of raw data from the internet. Fine-tuning. The general model is polished for specific tasks, like legal analysis or customer service, using smaller, specialized datasets. RLHF. Reinforcement learning from human feedback uses human rankings to align the model's outputs with human values and safety standards. Natural language processing, NLP, and large language models LLM are closely related but distinct concepts within the broader AI sector. NLP is the overarching field that involves the interaction between computers and human language. It includes tasks such as sentiment analysis, machine translation, speech recognition, and more. LLMs are a specific subset of NLP that focuses on using datasets and deep learning techniques to create models capable of generating and understanding human-like text. While NLP encompasses a broad range of applications, LLMs represent a cutting-edge approach within this field. They offer new possibilities for language-related tasks due to their scale and sophistication. The relationship between natural language processing, NLP, and large language models, LLMs, is not one of competence, but of hierarchy. NLP is the entire field of study, while an LLM is an advanced and specific tool within that field. NLP is the science of teaching machines to understand human language, and an LLM is the state-of-the-art engine used to achieve this on a large scale. The steps in LLM processing are: tokenization. The input text is broken down into smaller pieces, tokens, for processing. Training on large datasets, LLMs learn from massive text datasets, improving their language understanding. Attention mechanisms. The model determines the importance of each word relative to others in a sentence. And text generation. Using probability-based predictions, LLMs generate coherent and contextually relevant text. LLM models support generative AI models as a preliminary step to machine learning and artificial intelligence models. Search engine optimization. For a web page to rank well, experts usually work in these key areas. Technical SEO focuses on the infrastructure of the site, ensuring that search engines can crawl and index it correctly. It includes loading speed and mobile adaptability. Content creation of relevant and useful material that responds to the user's search intent. On-page SEO optimization of individual elements within the page, such as the use of keywords in titles, meta descriptions, headings, and descriptive URLs. Off-page SEO, off-site actions to increase your authority, mainly by obtaining quality links from other websites, backlinks. Generative artificial intelligence, Gen AI, is a type of AI that can create new content, such as text, images, audio, video, and computer code, by learning from vast amounts of existing data. Unlike traditional AI, which typically focuses on identifying patterns or classifying data into existing categories, Gen AI uses those patterns to produce entirely original outputs that often mimic human creativity. Gen AI models use deep learning and neural networks. They are trained on large datasets to understand the structure of information. Transformers, these are the architecture behind tools like ChatGPT and Gemini. They use a self-attention mechanism to weigh the importance of different parts of input data to generate contextually relevant text or code. Diffusion models, these are commonly used for high-quality image generation. They start with random noise and gradually refine it into a coherent image based on a user's prompt. Generative adversarial networks, GANs, these have two neural networks that compete against each other. One generates data while the other tries to detect if it is fake, pushing the generator to create increasingly realistic results. Variational autoencoders, VAEs, these models learn a compressed representation of data, latent space, and can sample from this space to generate new, similar data points. Key risks and ethical concerns. Despite its benefits, Gen AI presents several challenges that require careful oversight. Hallucinations. Models can confidently present false or fabricated information as fact. Bias. AI can inherit and amplify societal biases present in its training data. Intellectual property. Ongoing debates surround the use of copyrighted material for training and who owns the resulting AI-generated content. Security. Concerns include the creation of deepfakes for misinformation and the potential for new types of cyberattacks. Gen AI's journey began in the 60s with basic chatbots, marking the first foray of machines into text production. Today, it stands out as a leader in AI, generating high-quality text, images, and more. The key change occurred in 2014 with Generative Adversarial Networks, GANs, which revolutionized the field by creating realistic means like human creations. Today, innovations like OpenAI's o1 and ChatGPT, Microsoft's Phi 3.5 models, Mistral's Pixtral 12b, and many more, showcase its transformative impact on technology and human interaction. Gen AI has evolved from rule-based systems to advanced neural networks today. This transformation grants machines autonomy, enabling them to autonomously generate content once considered solely within human creativity. From its early stages to modern neural networks, Gen AI continues to redefine innovation and reshape our digital landscape with each stride. The new Gen AI have the potential to accelerate the adoption of AI, even for organizations that lack in-depth knowledge in AI. These models, although they require customization, can be integrated into tasks using minimal data through APIs or prompt engineering, generating content and ideas. Gen AI excels at producing diverse results, from video ads to novel proteins with antimicrobial properties. This ability drives innovation by generating new ideas and creative solutions that were previously solely driven by humans. These new possibilities are generating content and ideas, improving efficiency, and personalizing experiences. Gen AI represents a significant technological advancement, driving innovation, operational optimization, and personalized interactions across various industries. Its ability to reshape business strategies and enhance customer engagement marks a fundamental shift in the application of AI within industries. A generative adversarial network, GAN, is an artificial intelligence model where two neural networks compete to generate new, realistic data that mimics a training set. This architecture was introduced by Ian Goodfellow in 2014. Here's a breakdown of how this technology works and its applications for generating high-definition, HD, images. The system works like a zero-sum game between two networks. The component R. The generator acts as a faker. It takes random noise as input and creates samples of synthetic data, such as an image, trying to make them look real. The discriminator acts as the detective. It evaluates the images and determines if they are real, from the original dataset, or fake, created by the generator. Training. The generator tries to deceive the discriminator, and the discriminator tries not to be deceived. Both continually improve until the discriminator can no longer distinguish the real from the false. GAN is a class of machine learning frameworks. A system of two competing neural networks implements GANs in unsupervised machine learning. This setup helps in capturing or reproducing the variability and features of a given dataset. RAG, Retrieval Augmented Generation, in GPT is a technique that combines the text generation capability of GPT models with an external information search system. Rather than relying solely on what the model learned during its training, the system queries a database to respond with accurate, up-to-date, or proprietary data. Why is RAG necessary? Base GPT models have important limitations that this architecture helps to solve. Static information. They are not aware of events after their training cutoff date. Lack of private data. They don't have access to your manuals, internal documents, or databases. Hallucinations. Sometimes they invent answers in a very convincing way when they do not know a fact. RAG highlights a balance, simplicity versus precision. While GPT stands out for its ease of deployment, incorporating RAG unlocks transformative applications, from real-time customer support to adaptive learning systems. The challenge is to balance computational efficiency with the demands of dynamic recovery. One distinction between GPT and RAG lies in the contextual approach. GPT generates answers based on pre-trained data, excelling in fluency, but often lacking accuracy in dynamic and/or specialized scenarios. RAG, on the other hand, retrieves real-time information from external sources, ensuring that responses are accurate and context-based. This makes RAG especially effective in fields such as medicine, where up-to-date research is non-negotiable. RAG's reliance on external databases introduces challenges, such as latency and data quality control. For example, in customer support, RAG can retrieve real-time product details, but it risks inaccuracies if the data is outdated. GPT avoids this problem but sacrifices adaptability, limiting its usefulness in rapidly evolving domains. Integrating RAG into GPT could create a hybrid model, combining generative fluency with real-time accuracy. This approach could bridge the gap between static and dynamic AI systems. RAG is made up of 3 steps. Recovery: AI first searches for relevant information in connected sources, such as policy documents, product manuals, or internal FAQs. Augmentation: the retrieved content is fed into the AI model as additional context. This step is what makes RAG special. The model is not based solely on what it knows from training, it receives enriched information in real time to base its response. Generation: using this combination, its internal language capabilities plus the retrieved data, the AI produces a natural language response. RAG allows AI to remain accurate, context-aware, and aligned with current knowledge, without having to retrain the model. Case: use of retrieval-augmented generation in Salesforce, to improve the quality and relevance of the content generated by its AI models. The implementation of RAG leverages Salesforce's Data Cloud and Einstein Copilot Search to retrieve and integrate structured and unstructured data, ensuring that the content generated is accurate, contextually relevant, and up-to-date. Since 2025, Einstein Copilot is known as Agentforce. Implementation: the implementation begins with the Data Cloud, which unifies data from various sources, including emails, call transcripts, PDFs, and other unstructured formats. This data is transformed into vector embeddings using a specialized model through the Einstein Trust Layer. When a content generation request is made, the system performs a semantic search to retrieve the most relevant chunks of data. These fragments construct an augmented prompt fed into an LLM. The LLM generates the final content from this augmented prompt, ensuring that the output is accurate and contextually appropriate. A vector database supports this process, facilitating efficient data retrieval and integration. Result: Salesforce's RAG implementation has improved content quality by integrating real-time, context-specific information, resulting in higher user satisfaction and interaction rates. This improvement in efficiency is complemented by better search engine optimization, SEO, performance, which leads to better search engine rankings and increased organic traffic. RAG highlights a balance: simplicity versus precision. While GPT stands out for its ease of deployment, incorporating RAG unlocks transformative applications, from real-time customer support to adaptive learning systems. The challenge is to balance computational efficiency with the demands of dynamic recovery. One distinction between GPT and RAG lies in the contextual approach. GPT generates answers based on pre-trained data, excelling in fluency, but often lacking accuracy in dynamic and/or specialized scenarios. RAG, on the other hand, retrieves real-time information from external sources, ensuring that responses are accurate and context-based. This makes RAG especially effective in fields such as medicine, where up-to-date research is non-negotiable. RAG's reliance on external databases introduces challenges, such as latency and data quality control. For example, in customer support, RAG can retrieve real-time product details, but it risks inaccuracies if the data is outdated. GPT avoids this problem but sacrifices adaptability, limiting its usefulness in rapidly evolving domains. Integrating RAG into GPT could create a hybrid model, combining generative fluency with real-time accuracy. This approach could bridge the gap between static and dynamic AI systems. Agents in GPT are artificial intelligence systems that use language models to execute tasks autonomously. Unlike a traditional chat that only answers questions, an agent can reason, plan, and use tools to complete complex workflows. A GPT agent is based on three fundamental pillars. Model, the brain, such as GPT-4o or GPT-5, that processes information and makes decisions. Tools, APIs or functions that allow you to interact with the outside world, search the web, send emails, execute code. Instructions, clear guidelines and boundaries that define your behavior and your goal. GPT agent allows the user to perform complex tasks, online, as if he or she were the one executing them. A GPT agent can combine actions between reasonings, if the user considers that it has that function that allows them to immerse themselves in another publication and debate, and the action of conducting research on public websites, uploaded files, and third-party sources, such as email repositories or documents. The agent can also perform actions such as filling out forms and editing spreadsheets. In other words, GPT, in addition to its models, now has a tool that allows the creation of automated processes with a certain scope and control. Evolution of Retrieval Augmented Generation. Native RAG. Using RAG to obtain information from an external source of knowledge, allows LLMs to answer questions by extracting relevant information from private or unpublished documents. RAG is good at providing specific answers by getting accurate information. However, RAG struggles with broader, more global questions like what are the main themes of the dataset? Because these questions require understanding and summarizing the entire text, rather than simply finding specific information. These questions fall under the Query Focus Summary, QFS, for which RAG is not designed. Graph RAG. Graph RAG is a method that combines two important tasks, retrieving information and summarizing it, using a graph-based approach. One of its features is to provide an overview of the data structure, before questions are asked. It achieves this by identifying communities of closely connected nodes, dividing the graph into multiple levels, from broad topics to specific topics. Graph RAG creates an entity knowledge graph from source documents, linking related pieces of information. It then generates summaries for groups of related entities, helping users understand the broader topics. When a user asks a question, Graph RAG uses these summaries to form partial answers, which are then combined into a final answer. Graph RAG is designed to address complex and general questions, offering a more complete view of the data, but requires a considerable amount of computational resources to function effectively. Memory RAG. Memory RAG improves on traditional RAG by integrating a memory mechanism that allows context to be preserved from previous interactions, helping you provide more relevant and context-aware responses over time. By remembering key details of a conversation, Memory RAG can deliver responses that are more consistent and personalized, improving the user experience by making conversations more continuous and relevant. However, memory and computational resources must be managed to ensure optimal performance. Although it's better at retaining context, you may still struggle with complex summarizing tasks like global question answering. Agentic RAG. Unlike the traditional RAG, which focuses solely on retrieving and augmenting data for response generation, the agentic RAG introduces decision-making capabilities, empowering the LLM to act as an intelligent agent that not only retrieves data, but actively determines how to process a query, which sources to access, and how to format the response. Agentic RAG is an advanced AI architecture that transforms RAG's standard pipeline from a linear process into an autonomous decision-making system. In a traditional RAG system, the process is static, it receives a query, retrieves documents, and generates a response. However, the agentic RAG uses a large language model, LLM, as an intelligent agent that can plan, reason, and use tools to ensure the most accurate output. Key features. Autonomous reasoning. The agent decides which tools or databases to query based on the user's specific intent. Multi-step planning. Unlike a single-step system, the agent can break down complex questions into smaller tasks and execute them sequentially, or in parallel. Self-correction. The agent can assess the quality of the information retrieved and, if it is insufficient, refine the search or try a different approach. Tool integration. You can interact with external APIs, code interpreters, or multiple specialized vector databases. Agentic RAG is an advanced AI architecture that transforms RAG's standard pipeline from a linear process into an autonomous decision-making system. In a traditional RAG system, the process is static. It receives a query, retrieves documents, and generates a response. However, the agentic RAG uses a large language model, LLM, as an intelligent agent that can plan, reason, and use tools to ensure the most accurate output. Key features: autonomous reasoning. The agent decides which tools or databases to query based on the user's specific intent. Multi-step planning. Unlike a single-step system, the agent can break down complex questions into smaller tasks and execute them sequentially, or in parallel. Self-correction. The agent can assess the quality of the information retrieved and, if it is insufficient, refine the search or try a different approach. Tool integration. You can interact with external APIs, code interpreters, or multiple specialized vector databases. Agentic RAG is not a single architecture. It's a spectrum of patterns, each adding decision-making at different points in the retrieval process. These are conditional, one-step. The simplest form of agentic behavior is deciding whether to retrieve at all. Before any retrieval happens, the model evaluates the query. Can this be answered from the model's training data? Does it require current information? Is it a calculation or reasoning task that does not need retrieval? Based on this assessment, the system either skips the recovery, and generates directly, or recovers it once and then generates. Iterative, multi-step. Sometimes the first retrieval isn't enough. The system retrieves, evaluates the results, and decides whether to retrieve again with a refined query. Tool routing. Many applications have multiple retrieval sources, documentation databases, APIs, search engines, and user databases. Tool routing systems analyze the query and decide which sources to use. Agentic RAG is an advanced AI architecture that transforms RAG's standard pipeline from a linear process into an autonomous decision-making system. In a traditional RAG system, the process is static. It receives a query, retrieves documents, and generates a response. However, the agentic RAG uses a large language model, LLM, as an intelligent agent that can plan, reason, and use tools to ensure the most accurate output. Key features: autonomous reasoning. The agent decides which tools or databases to query based on the user's specific intent. Multi-step planning. Unlike a single-step system, the agent can break down complex questions into smaller tasks and execute them sequentially, or in parallel. Self-correction. The agent can assess the quality of the information retrieved and, if it is insufficient, refine the search or try a different approach. Tool integration. You can interact with external APIs, code interpreters, or multiple specialized vector databases. Agentic RAG is a spectrum of patterns. Planning-based. For complex queries that need multiple steps in a specific order, planning-based systems create a plan before acting. The system breaks down the query into steps, determines what information each step needs, and then executes the plan. Reflective, self-evaluating. After generating a response, some systems evaluate their own output for accuracy and completeness before returning it to the user. Multi-agent. Multiple specialized agents work on different aspects of the query. A coordinator breaks the query into subtasks and assigns them to specialist agents. Each agent has its own context, tools, and instructions. Generative AI technologies are causing radical changes in the business world, giving companies a competitive advantage. To adapt to rapidly changing market conditions, keep up with digital transformation, and produce more innovative solutions, companies have invested in Gen AI, as it accelerates and improves efficiency in decision-making processes, from understanding customer needs to product development and marketing strategies. Several technology-producing companies have taken on the role of integrating generative AI into corporate operations by linking them to their CRM processes. The introduction of transformers models in artificial intelligence has brought about a monumental shift in the way machines understand, process, and generate human-like data. Previously, AI relied on sequential processing methods that struggled with long-term context, and computational efficiency. Today, transformers models serve as the backbone of the most advanced applications that we use every day. Understanding them requires analyzing the limitations of past technologies. Recurrent neural networks, RNNs, and long-term short-term memory networks, LSTMs, were the standard, but they processed data word for word. This made them slow and prone to forgetting the first parts of a sentence. The advent of transformers neural networks eliminated the sequential bottleneck, enabling parallel data processing, becoming the driving force behind modern digital innovation. The origins of transformer models in artificial intelligence can be traced back to a landmark 2017 research paper by Google, researchers titled "Attention is All You Need." This paper introduced a novel neural network architecture that abandoned recurrence in favor of an attention mechanism. This change was a breakthrough in the evolution of machine learning algorithms, demonstrating that machines could understand the context of a word based on surrounding words simultaneously, rather than sequentially. As transformer models evolved quickly, researchers were aware that this approach is incredibly scalable. The development of transformer models allowed engineers to train systems with unimaginably large datasets using parallel processing. This efficiency allowed deep learning models to grow exponentially in size and capacity, laying the foundation for the sophisticated AI transformer technology that currently dominates the tech industry. Transformer models' essential components. Layer normalization stabilizes training by normalizing activations across features, which reduces internal covariate shifts and improves convergence speed. During training, this normalization prevents sudden changes in feature magnitudes, making the learning process more consistent. Residual connections allows information to bypass multiple layers, improving gradient flow and preventing information loss. These connections are crucial in deep transformer stacks, where they ensure original information remains intact, and help mitigate vanishing gradient problems. Self-attention mechanism allows the model to consider all words in a sequence simultaneously, focusing on the most relevant ones regardless of position. Unlike sequential RNNs, it processes relationships between all words at once. Positional encoding. Since transformers don't process input sequentially, positional encoding preserves word order by adding positional information to word embeddings. This encoding uses sine and cosine functions. Multi-head attention. This feature applies self-attention multiple times in parallel, with each attention head learning different linguistic patterns. Some heads might focus on syntax, subject-verb relationships, while others capture semantics, word meanings. These parallel outputs are then concatenated into a unified representation. Feed-forward layers. Each transformer block contains feed-forward neural networks that process attention outputs. These consist of two connected layers with an activation function between them, that enhance feature representation by transforming the attention-weighted input. The encoder's job is to read the input data, like a sentence in English, and map it into a continuous mathematical representation, capturing all its contextual nuances. The decoder then takes this rich mathematical representation and generates the desired output, like translating that sentence into German. While some modern models use only the encoder, like the BERT model, or only the decoder, like GPT models, this fundamental two-part structure was crucial to the initial success of the architecture. The original transformer was built using an encoder-decoder structure. The encoder's job is to read the input data, like a sentence in English, and map it into a continuous mathematical representation, capturing all its contextual nuances. The decoder then takes this rich mathematical representation and generates the desired output, like translating that sentence into French. While some modern models use only the encoder, like the BERT model, or only the decoder, like GPT models, this fundamental two-part structure was crucial to the initial success of the architecture. How the transformers model works? The transformer model consists of an encoder and decoder, both built using multiple layers of self-attention and feed-forward networks. Input processing. The input text is tokenized and converted into word embeddings. Positional encodings are added to maintain word order information. Encoder takes input embeddings and applies multi-head self-attention. Utilizes positional encodings to maintain word order. Passes information through feed-forward layers for processing. Self-attention mechanism. The self-attention mechanism allows each word in a sentence to focus on other relevant words dynamically. Multi-head attention. Instead of a single attention mechanism, multi-head attention allows the model to capture different relationships within the input. Feed-forward neural network. Each encoder layer has a fully connected feed-forward network that processes attention outputs. Decoder. Receives encoder output along with target sequence. Uses masked self-attention to prevent looking ahead. Combines encoder-decoder attention to refine output predictions. Improving Language Understanding by Generative Pre-training is the seminal paper published by OpenAI in June 2018 that introduced the first Generative Pre-trained Transformer, GPT-1. The paper demonstrated that a single, task-agnostic model could achieve high performance across a wide range of natural language understanding, NLU, tasks by following a two-stage training procedure. The model uses a semi-supervised approach consisting of two phases. Unsupervised pre-training. The model is trained on a large, unlabeled corpus to predict the next word in a sequence. This stage allows the model to learn grammar, world knowledge, and long-range dependencies. Supervised fine-tuning. After pre-training, the model is adapted to specific downstream tasks, such as sentiment analysis, question answering, or textual entailment, using smaller, labeled datasets. Task-specific input transformations. For some tasks, such as text classification, the model can be adjusted directly with fine-tuning. Other tasks, such as answering questions or textual implications, have entries structured as ordered pairs of sentences or triples of documents, question and answer. Since the pre-trained model, GPT-1, was trained with contiguous sequences of text, some modifications are required to apply it to these tasks. Previous work proposed learning task-specific architectures about transferred representations. This approach reintroduces a significant amount of task-specific customization and does not use transfer learning for these additional architectural components. Instead, a walkthrough style approach is used, where we convert structured inputs into an ordered sequence that GPT-1 can process. These input transformations avoid making extensive changes to the architecture between tasks. Below is a brief description of these input transformations, that include adding randomly initialized tokens, S&E. Textual implication. For implication tasks, we concatenate the sequences of the P premise and the hypothesis H tokens, with a delimiter token, less than greater than between them. Similarity. For similarity tasks, there is no inherent order of the two sentences being compared. To reflect this, the input sequence is modified to contain both possible sentence orders, with an intermediate delimiter, and each is processed independently to produce two sequence representations that are summed item by element before being fed into the linear output layer. Answers to questions and common sense reasoning. For these tasks, GPT-1 selected a Z context document, a Q question, and a set of possible fake answers. We concatenate the context document with the question for each possible answer, adding a delimiter token. GPT-1 independently processes each of these sequences and then normalizes it using a softmax layer, to produce an output distribution on possible answers. Summary of the GPT workflow. Tokenization. Your prompt is broken into tokens, chunks of characters. Embedding. Tokens are converted into numerical vectors that represent their meaning in a multidimensional space. Positional encoding. Because transformers process data in parallel, positional markers are added so the model knows the order of the words. Processing. The data passes through multiple layers of self-attention to determine the significance and context of each word. Softmax layer. The final layer produces a probability distribution to pick the next most likely token. From ANN to GPT models, tracing the evolution of AI language models. In 1998, the LeNet 5 architecture was first presented in the article Gradient-Based Learning Applied to Document Recognition by Yann LeCun et al. They showed that convolutional neural networks are effective for handwritten digit recognition tasks. The figure shows an example of an artificial neural network with 8 input units, 4 output units, and 2 blocks of size 2 memory cells. The figure shows the transformer architecture and training objectives. The figure at right shows the input transformations for fine-tuning on different tasks. All structured inputs are converted into token sequences to be processed by the pre-trained model, followed by a linear plus softmax layer. 4 steps are followed: classification, entailment, similarity, and multiple choice. 2 approach are considered: race in answers to questions, and multi-NLI in textual implication. The figure illustrates the performance of the multi-NLI and race as a function of the number of layers transferred. We observe the standard result that transferring embeddings improves performance, and that each transformer layer provides further benefits up to 9% for full transfer on multi-NLI. This indicates that each layer in the pre-trained model contains useful functionality for solving target tasks. The right figure shows the evolution of zero-shot performance on different tasks as a function of LM pre-training updates. Performance per task is normalized between a random guess baseline and the current state-of-the-art with a single model. Attention is all you need, published by Google, is the key paper of the actual GPT. Prior to GPT, recurrent neural networks, short-term memory, and recurrent neural networks with blocks had established themselves as cutting-edge approaches in modeling sequences and transduction problems, such as language and machine translation. Since then, numerous efforts have continued to push the boundaries of recurring language models and encoder-decoder architectures. Recurrent models factor the calculation along the symbol positions of the input and output sequences. By aligning the positions with the steps in the calculation time, they generate a sequence of hidden states, based on the previous hidden state in the input for the last position. This inherently sequential nature prevents parallelization in training, which becomes critical in longer sequences, as memory limitations limit clustering between examples. The fundamental constraint is sequential calculation. Attention mechanisms have become an integral part of modeling sequences and transductions in various tasks, allowing dependencies to be modeled regardless of their distance in input or output sequences. In all but a few cases, such mechanisms are used in conjunction with a recurring network. The authors propose the transformer, a model architecture that avoids recurrence and relies entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly greater parallelization and can reach a new state-of-the-art in translation quality after being trained for just 12 hours on 8P100 GPUs. Beginning in 2014, the graph shows a timeline of the articles in GPT. GPT, with companies like OpenAI and Anthropic, has produced the fastest growing of artificial models in history. Although it may seem so on the surface, this progress does not occur in a vacuum and overnight. Under the cover, there are gradual advances that eventually culminate in such an event. Before 2020, there was a lot of activity in terms of papers, after which many other important developments have emerged, as these models continue to acquire new capabilities and improve their performance. Encoder and decoder stacks. Encoder. The encoder is composed of a stack of 6 identical layers that have 2 sublayers. The first is a multi-head self-attention mechanism, and the second is a fully connected and positioned simple direct feed network. A residual connection is employed around each of the 2 sublayers, followed by their layer normalization. That is, the output of each sublayer is the layer norm, x plus sublayer x, where sublayer, x, is the function implemented by the sublayer itself. To facilitate these residual connections, all sublayers of the model, as well as the embedding layers, produce outputs of dimension model equal to 512. Decoder. The decoder is also made up of a stack of 6 identical layers. In addition to the 2 sublayers in each encoder layer, the decoder inserts a third sublayer, which performs multi-head attention on the output of the encoder stack. Like the encoder, residual connections are employed around each of the sublayers, followed by layer normalization. The self-attention sublayer in the decoder stack is modified to prevent positions from paying attention to the following positions. This masking, combined with the fact that the output inlays are shifted at one position, ensures that predictions for position I can only depend on known outputs at positions smaller than I. The figure shows the transformer model architecture, that follows this overall architecture using stacked self-attention and pointwise, fully connected layers for both the encoder and decoder. Most competitive neural sequence transduction models have an encoder-decoder structure. The encoder maps an input sequence of symbol representations to a sequence of continuous representations. Given the continuous representations, the decoder then generates an output sequence of symbols one element at a time. At each step, the model is autoregressive, consuming the previously generated symbols as additional input when generating the next. The transformer follows this overall architecture using stacked self-attention and pointwise, fully connected layers for both the encoder and decoder, shown in the left and right halves of the figure, respectively. An attention function can be described as mapping a query and a set of key-value pairs to an output, where the query, keys, values, and output are all vectors. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. The left image introduces the scaled dot product attention, the right introduces the multi-head attention, which consists of several layers of attention running in parallel. In the attention encoder-decoder layers, queries come from the previous decoder layer, and keys and memory values come from the output of the encoder. This allows all decoder positions to be overall positions in the input stream. This mimics typical encoder-decoder attention mechanisms in sequence-to-sequence models. The encoder contains layers of self-attention. In an attention layer, all keys, values, and queries come from the same place, in this case, from the output of the previous layer in the encoder. Each position in the encoder can serve all positions in the previous layer of the encoder. Similarly, the decoder's self-care layers allow each decoder position to adapt to all positions up to and including that position. We need to avoid the flow of information to the left in the decoder to preserve the autoregressive property. We implemented this within scaled attention by hiding all values in the softmax input that correspond to illegal connections. In practice, the attention function is calculated for a set of concurrent queries, packaged in a Q matrix. Keys and values are also packaged in K and V matrices. The figure shows the scaled dot product attention. The input consists of queries and dk dimension keys, and dv dimension values. The scalar products of the query are calculated with all the keys, each is divided into the square root of dk, and a softmax function is applied to obtain the weights of the values. The attention function of a set of queries, packaged in the Q matrix, is calculated simultaneously. Keys and values are also packaged in K and V matrices. The figure shows the multi-head attention consists of several attention layers running in parallel. Instead of performing a single attention function with keys, values, and dimensional queries from D models, we find it beneficial to linearly project queries, keys, and H values times with different learned linear projections dk and dv, respectively. On each of these projected versions of queries, keys and values we then perform the attention function in parallel, yielding dv dimensional output values. A generative pre-trained transformer, GPT, is a type of large language model, LLM, that uses a specific neural network architecture to understand and generate human-like text. The theory behind GPT is built on three core pillars. 1. Generative. The generative aspect refers to the model's primary goal, creating new content rather than just classifying existing data. Autoregressive prediction. GPT operates by predicting the next most probable word, or token, in a sequence based on all preceding words. Sequential generation. Once a token is predicted, it is added back to the input, and the process repeats until a complete response is formed or an end token is reached. 2. Pre-trained. The learning process. Before a GPT model can follow specific instructions, it undergoes a massive phase of unsupervised learning. Massive datasets. The model is fed billions of pages from the internet, books, and articles. Self-supervised learning. It learns the statistical structure of language, grammar, facts, reasoning, by trying to predict the next word in these texts without human-labeled help. Fine-tuning. After pre-training, models are often refined using reinforcement learning from human feedback, RLHF, to align their responses with human values and safety. 3. Transformer, the architecture. The transformer is the underlying deep learning engine, first introduced in the 2017 Google paper. Attention is all you need. Self-attention mechanism, this is the brain of the model. It allows the GPT to attend to different parts of a sentence simultaneously to understand context. For example, it can link a pronoun at the end of a long paragraph back to its original subject. Decoder-only design, unlike some transformers that use both encoders and decoders, GPT specifically uses a stack of decoder blocks optimized for generating text one step at a time. Parallel processing, this architecture allows the model to process large amounts of data in parallel rather than one word at a time, making training much faster. How does GPT work? The GPT models are based on the transformer architecture, introduced in 2017, which uses self-service mechanisms to process input data in parallel, enabling efficient handling of long-range dependencies in text. The core process involves pre-training. The model is trained on large amounts of textual data to learn patterns of language, grammar, facts, and some reasoning skills. Supervised fine-tuning, the model is trained on specific datasets, with human feedback, to align its responses with the desired outcomes. Reinforcing learning from human feedback, RLHF. This approach allows GPT to generate coherent and contextually relevant responses across a wide variety of topics and tasks. GPT is an advanced deep learning model, designed to comprehend and create human-like text based on the patterns it picks up after learning from vast amounts of text dataset during the pre-training phase. Key characteristics. Generative GPT can develop coherent and contextually relevant text based on the given prompt, ranging from a few words to entire paragraphs. Based on the prompts, GPT can produce responses based on various tones and styles, variations or a continuation of the prompt. Even a slight change in the prompt guarantees a different response generated by GPT. After all, GPT's generational capability stems from the context it detects from the prompt. Pre-trained, the pre-training phase is a pivotal point where GPT gains language understanding by predicting the next word in sentences. This step enables it to understand grammar and syntax and gain word knowledge. After this pre-training phase, GPT can be fine-tuned to perform specified tasks. Overall, the objective of pre-training is for GPT to learn the intricacies of language from large datasets. Transformer GPT is based on the transformer architecture, a type of neural network architecture that excels at processing sequential data, such as sentences, phrases, paragraphs and so on. Due to this ability, combined with the architecture's efficiency, the transformer architecture is currently the most widely adopted architecture for multiple natural language processing, NLP, tasks. From GPT-1 to ChatGPT, evolution of the Generative Pre-trained Transformer. In recent years, AI has come to the forefront of technological innovation, and among its most impressive feats is natural language processing, NLP. The Generative Pre-trained Transformer, or GPT, series by OpenAI stands as a testament to how far NLP has come. Let's embark on a journey from GPT-1 to the current marvel, ChatGPT, and witness the evolution of a technology that's transforming our digital conversations. GPT-1, the Genesis. Launched in June 2018, GPT-1 was the first in a series that aimed to revolutionize machine understanding of human language. With 117M parameters, it was trained on the book's corpus dataset. GPT-1 showcased the potential of transformers, a novel type of deep learning model, in handling a range of NLP tasks without task-specific training. GPT-2, the breakthrough. Scaling up. The world took notice when OpenAI introduced GPT-2 in February 2019. Boasting 1.5 billion parameters, this model was a giant leap from its predecessor. OpenAI initially withheld the full model, citing concerns about potential misuse. GPT-2 demonstrated capabilities in tasks like translation, question answering, and even rudimentary reading comprehension. Its ability to generate coherent, diverse, and contextually relevant paragraphs of text was particularly striking. GPT-3, The game changer. Deep learning breakthrough. 2020 witnessed the release of GPT-3, the third iteration, and it dwarfed its predecessor with a whopping 175 billion parameters. Its vast scale and extensive training on diverse internet text allowed for unprecedented capabilities. GPT-3 could draft essays, answer questions, create poetry, and even code in Python. The model's adaptability led to a myriad of applications, from content creation to customer service bots. ChatGPT, fine-tuning excellence. Conversational mastering. Building on the foundation of GPT-3, ChatGPT was designed with a specific focus on improving conversational abilities. By fine-tuning GPT-3 on a mixture of licensed data, data created by human trainers, and other sources, ChatGPT showcased a nuanced understanding of user prompts. This iteration was a nod to the growing demand for chatbots and conversational agents in various industries. GPT-4, Generative Pre-trained Transformer 4, is an advanced artificial intelligence model developed by OpenAI, officially launched on March 14, 2023. It distinguishes itself from its predecessors by being a multimodal system, which means that it can process and understand both text and images to generate detailed responses. Key capabilities. Multimodality: you can analyze graphics, photos, and documents with images to solve complex problems. Larger context window: supports entries of more than 25,000 words, making it easier to analyze long texts and lengthy conversations. Advanced reasoning: has demonstrated superior performance on academic and professional exams, such as advocacy tests or advanced math, and enhanced creativity: uses more natural language, metaphors, and can adopt specific writing styles more accurately. The table specifications of GPT models shows the following data: model name, year released, architecture, and number of parameters. The speed of growth of the number of parameters is impressive. To solve the model, it requires high computational power. During the 2010s, improved machine learning algorithms, more powerful computers, and an increase in the amount of digitized material allowed for an AI boom. Separately, the concept of generative pre-training, GP, was a long-established technique in machine learning. GP is a form of self-supervised learning wherein a model is first trained on a large, unlabeled dataset, the pre-training step, to learn to generate data points. This pre-trained model is then adapted to a specific task using a labeled dataset, the fine-tuning step. The transformer architecture for deep learning is the core technology of a GPT. Developed by researchers at Google, it was introduced in the paper Attention is All You Need, which was released on June 12, 2017. The transformer architecture solved many of the performance issues that were associated with older recurrent neural network, RNN, designs for natural language processing, NLP. The architecture's use of an attention mechanism allows models to process entire sequences of text at once, enabling the training of much larger and more sophisticated models. Since 2017, available transformer-based NLP systems have been capable of processing, mining, organizing, connecting, contrasting, and summarizing texts as well as answering questions from textual input. GPT architecture. Input embedding. Input. The raw text input is tokenized into individual tokens, words or subwords. Embedding. Each token is converted into a dense vector representation using an embedding layer. Positional encoding. Since transformers do not inherently understand the order of tokens, positional encodings are added to the input embeddings to retain the sequence information. Dropout layer. A dropout layer is applied to the embeddings to prevent overfitting during training. Transformer blocks. Layer norm. Each transformer block starts with a layer normalization. Multi-head self-attention. Multi-head self-attention are core component where the input passes through multiple attention heads. Add and norm. The output of the attention mechanism is added back to the input, residual connection, and normalized again. Feed-forward network. A position-wise feed-forward network is applied, typically consisting of two linear transformations with a GE-LU activation in between. Dropout. Dropout is applied to the feed-forward network output. Layer stack. the transformer blocks are stacked to form a deeper model, allowing the network to capture more complex patterns and dependencies in the input. Final layers. Layer norm. Layer norm is final layer normalization is applied. Linear, the output is passed through a linear layer to map it to the vocabulary size. Softmax. A softmax layer is applied to produce the final probabilities for each token in the vocabulary. The figure shows the diagram of how GPT performs feature extraction, data augmentation, and synthetic data generation. Feature extraction leverages the GPT advanced knowledge of language, and filters key information from textual data for use in machine learning applications. Data augmentation enhances datasets by generating varied and semantically similar textual content, thereby improving the diversity and robustness of data, to train machine learning models. Synthetic data generation creates artificial data that mimics real-world datasets, using them to train machine learning models, when real data may be scarce or sensitive. As the figure shows, before the GPT era, various NLP techniques such as entity recognition, sentiment analysis, and category classifications were used to extract textual data, such as social media posts. Subsequently, the extracted characteristics were used by machine learning techniques to obtain information and analysis. With the advent of GPT, it was possible to extract features with a simple prompt, for example, by categorizing the data into animals, plants, and equipment. GPT, a regression model. A small example of the power of computation is the case of regression models, which comes from genetics and was popularized by Sir Francis Galton in the late 19th century, with the publication of Regression Towards Mediocrity and Hereditary Stature. Today it is one of the fundamental techniques of predictive AI, parameter identification, but its concepts and limitations have not changed. They are: the number of observations must be greater than the number of parameters to be adjusted. The greater the number of parameters, the better models are generated in terms of goodness of fit, and if the number of observations is greater than the parameters, there will be redundant observations, which if used in the regression will produce confusion in the results to be obtained. In the origins of computing, the problem was the observation storage capacity, the power required to execute the process, that depending on the methodology, requires the inversion of a matrix of the size of the observations. With these constraints, estimating a model of thousands of parameters was a challenge. With the progress of computation, also evolved methodologies, estimation algorithms, until today to the conjunction of computing power and algorithmic power, which gives direction to the effective application of GPT models, which in practice permanently estimate models of hundreds of thousands, or millions of parameters. In the same way, will grow the power of prescriptive AI. Normally, in regression models, one of the main concerns is the sample size. Due to its smallness, this leads to low efficiency measures for regression quality indicators. But in GPT everything is different. Tech companies like OpenAI, considering that everything is on the web, made the decision to digitize the public content of the web to improve accuracy with an ever-growing sample. The growth in the number of parameters is directly related to the sample size. With this policy, GPT will have larger and larger public samples, require more parameters, and the day will come when all the available sample will have been consumed. Over time, the new sample content does not add value, as it corresponds to roughly duplicate data. What will happen that day? In theory, public GPT would have a universal model of known data that can no longer grow. Prompt engineering is the skill of writing clear instructions for an AI system that allows it to produce exactly what you need. Prompt engineering. Prompt engineering is the discipline of designing, optimizing, and refining the inputs, instructions or prompts, given to an artificial GPT to obtain accurate and high-quality results. It is considered both an art and a science, as it combines linguistic clarity with a technical understanding of how language models, LLMs, process information. There are several strategies to improve AI responses. Zero-shot prompting, asking for something directly without giving previous examples. Few-shot prompting, Provide the model with some examples of the desired tasks so that they understand the pattern. Chain of thought, asking AI to think step by step to solve complex reasoning problems. Role prompting, assign a specific role to the AI, when acting as a marketer, to adjust its tone and perspective. Prompt chaining, breaking down a complex task into several steps, using the output of one prompt as input for the next. Prompt engineering important techniques. Arithmetic validation, when math becomes truth, algorithmic protocols, replaces trial with steps, granular documentation, force proof of execution, chain of thought, make reasoning visible, thought tree, explore before committing, react, reasoning plus action loops, self-consistency, generate multiple paths, choose the best, meta-prompting, let the AI design its own instructions, zero shot versus few shots, when examples help, when they hurt, and reasoning models, why they are different. Reverse prompt engineering consists of showing GPT a result, a text or an image, and asking it to deduce which was the original prompt that generated it. For the text, you copy a writing style you like and tell the GPT, analyze this text and generate the prompt that would produce it. This allows you to learn the formula behind high-quality content. For images, tools such as Clip Interrogator are used to extract keywords, artist styles, and technical descriptions from an existing image, and thus recreate similar prompts. Security and detection. There are frameworks such as iPad, Inverse Prompt for AI detection, that use this technique to verify whether a text was written by a person or by an AI, analyzing whether the text matches the inverted prompt that the tool reconstructs. Reverse prompt engineering, RPE, is a new step to generative AI. It may be used as a powerful tool for different business categories, starting from super small startups and finishing with large enterprises. Each knowledge task follows the same basic flow. The modeler starts with inputs, performs some sort of reasoning or synthesis, and produces a result that he will share. The first phase assumes that the modeler already has a solid example of finished work. The modeler takes the original inputs and final output and asks the LLM to reverse engineer the prompt that can reliably produce similar results. The LLM looks at what went in, what went out, and how decisions were made. The result is a reusable meta-prompt. A meta-prompt is not content. It is instruction. It encodes structure, tone, constraints, quality thresholds, and decision rules that would otherwise only live in the human head. Once created, this meta-prompt becomes an asset. It can be reused whenever the same type of task appears again. Phase 2 is where the actual work gets done. Instead of starting from a blank page, the modeler starts with the reusable meta-prompt and new entries. The LLM may request clarification or additional context, which the modeler provide. It then generates a first-pass output aligned with the original quality standard. At this point, the human role changes. The modeler no longer writing from scratch, he/she reviewing, adjusting, and applying context. This separation matters. LLMs excel at structure and repetition. Humans excel at judgment and complexity. The moment the prompt stopped working, I didn't suddenly get bad at prompting. I got tired. For a while, I was very much into the game, tweaking phrases as if it were a competitive sport. Add more context. Eliminate adjectives. Move the constraints to the top. Try a different shade. He adds think step by step. Eliminate think step by step. I repeat. If you've read the official prompt guides, such as OpenAI's documentation, you know how it goes. Be clear. Be structured. Provide examples. Iterate. And it works. Until it stops. The breaking point was not a catastrophic failure. It was something smaller and more annoying. A model update quietly changed the behavior of my carefully crafted prompt. The same detail. The same entrance. Slightly different output. And suddenly I were rewriting the spell book. GPT Expert Committee. A GPT expert committee primarily refers to an advanced prompt engineering technique designed to simulate a panel of virtual specialists collaborating with each other to solve a complex problem. Instead of asking AI to respond generically, it is commanded to divide its logic into multiple expert roles that debate, refine, and consolidate an optimal solution. To activate this behavior in ChatGPT, a systematic structure based on the assignment of roles and workflows is used. Initial context defines the problem or central objective of the query. Committee assignment: appoint 3 or 4 expert profiles with complementary perspectives to address the topic. Workflow discussion: each expert generates their initial analysis independently. Experts review each other's proposals, highlighting blind spots or areas for improvement. Consolidation: a moderator unifies the conclusions into a final verdict or plan free of contradictions. Advantages of the GPT Expert Committee: reduces hallucinations, forcing the model to question itself, self-criticism, significantly decreases factual errors. Breadth of perspectives: avoid linear responses by forcing a multidimensional analysis, financial, technical, human, etc. Greater depth: elevates the technical quality and clarity of the result compared to a simple prompt. GPG: the intelligence loop. A reasoning loop in GPT, also known as a hallucinations loop, occurs when the model gets stuck repeating the same logic, phrases, or analysis steps without arriving at a final answer. This can happen both at a technical level in advanced reasoning-oriented models, and in the psychological interaction between the user and the AI. Loops in thinking models. Loops in models with native step-by-step analysis capabilities use an internal chain of thought. Sometimes, the thinking token extends infinitely because the model evaluates its own logical errors and starts the calculation again in an infinite cycle. The level of thought effort is set to extended or max for a problem that does not have a clear binary solution. At the user level, it refers to the use of GPT to process anxiety, or repetitive patterns of intrusive thoughts. Thought partner: set up AI to act as a belief auditor that confronts your own cognitive biases and breaks your cycles of mental rumination. Mental ventilation: using chat to transcribe and externalize repetitive ideas, brain dump, to reduce brain alertness. How to break a technical loop in GPT? If the artificial intelligence is trapped generating repetitive text or overanalyzing without giving a conclusion, apply the following strategies. Reduces the level of thinking: change the toggle to standard or light mode to force a more direct and faster response. Introduces strict restrictions. Add phrases such as limit your analysis to a maximum of 3 steps and generate the conclusion immediately in the prompt. Fix the bias on a new turn: if you spot the error, type "you've got stuck in a smooth loop over point X, ignore that step, and move on to the end result." Start a clean chat: loops often pollute the context window. Opening a new conversation clears the memory of the bad cycle. Using Generative Pre-trained Transformers. Public GPT versus Enterprise GPT. As technologies like ChatGPT and DeepSeek become household names, companies are increasingly exploring how generative pre-trained transformer models can revolutionize their business processes. However, there is a significant distinction between enterprise GPT and public GPT models that every executive should consider. There are 5 main differences. Public GPT, 5 main differences. Data security and privacy. These models operate on external servers, which poses risks when processing proprietary or sensitive information. Data governance is often a concern, especially in highly regulated industries. Implementation cost and operational costs. Lower upfront costs with subscription or usage models. However, unpredictable costs can arise as usage grows. While operating costs may seem lower, a lack of custom automation and efficiency improvements could result in hidden costs over time. Customization and control. It is based on public data and pre-trained insights. Adaptation to specific business contexts is limited, making it difficult to achieve full operational efficiency. Successful implementation, risk management, and return on investment. It is easier to deploy for general use, but enterprise adoption requires additional layers of development, which can introduce risks and dependencies on third-party solutions. ROI is often indirect and less predictable, as these models are not designed for specific business cases. Sustainability and long-term impact. While effective for immediate needs and experimentation, the sustainability of models in a business context is limited. The need for constant adaptation, compliance issues, and a lack of custom optimization all affect long-term strategic alignment. Enterprise GPT, 5 main differences. Data security and privacy. It operates in a secure, enterprise-grade environment, ensuring that sensitive data never leaves the organization's control. Fully customizable with internal data sets, aligning with compliance and regulatory needs. Implementation cost and operational costs. The initial setup and infrastructure investment may be larger, but customized solutions lead to a higher return on investment, ROI, in the long run. While operational costs include infrastructure maintenance, training, and upgrades, they are balanced with increased efficiency and optimized resource allocation. Customization and control. Enables deep integration with internal systems and applications. Custom models can be tuned with proprietary data to generate unique business insights and process automation. Control over the deployment environment improves operational consistency. Successful implementation, risk management, and return on investment. The implementation is backed by dedicated support, robust testing, and integration methodologies tailored to the business environment. Businesses can achieve a higher and more predictable ROI through increased productivity, a better customer experience, and streamlined operations. Sustainability and long-term impact. It offers a sustainable approach by enabling continuous learning and optimization within a controlled environment. As business models evolve, Enterprise GPT adapts and stays aligned, contributing to long-term digital transformation. Public GPT versus Enterprise GPT. While GPT models such as ChatGPT and DeepSeek offer an excellent entry point to generative AI, Enterprise GPT represents a strategic leap towards the digital transformation of enterprises, as it is the basis for assessing whether the organization is ready for customized, secure, and scalable solutions that align with business objectives. For organizations looking to transform not only processes, but also generate a measurable return on investment, reduce operational costs, and build a sustainable competitive advantage, investing in Enterprise GPT is a critical step. Generative Pre-trained Transformers. Public users of Public GPT. Massification of ideas. A lot of ideas go into GPT, comes out one. GPT drives cognitive synthesis and the trend toward homogenization that occurs when using large-scale language models. In artificial intelligence, the synthesis funnel is the phenomenon in which many ideas enter and only one comes out. This is due to the architecture of GPT models. The process can be described as data compression. During its training, the model processes trillions of text fragments, ideas, facts, styles, and converts them into mathematical vectors or embeddings. Statistical prediction. Instead of choosing the right idea, the model calculates the answer with the highest statistical probability, based on the patterns it has learned, acting as a filter that discards the less common options in favor of majority statistical consensus. With this approach, creating a new idea is impossible. Noise removal. The synthesis process helps to control fragmented information, transforming disordered data into a coherent and structured narrative, but unique. Massification has critical side effects on diversity of thought and knowledge. Homogenization of thought. By favoring the most frequent patterns, AI tends to produce average or generic content, which dilutes individual creativity and minority voices. Creative illusion. Studies suggest that although GPT generates ideas quickly, most can be repetitive or similar, lacking the diversity that human critical thinking brings. Confirmation bias. The model is optimized to give answers that are satisfactory to the user, often leading to constant self-validation rather than challenging ideas with conflicting perspectives. GPT forgets that, for Henrik Ibsen, in scientific thought the majority is never right. The phrase "the majority is never right" is a famous statement by playwright Henrik Ibsen, who argues that the dominant opinion often prioritizes comfort, conformity, or popularity over objective truth. Ibsen asserts that conventional wisdom, or popular consensus, is often flawed and that progress comes from minority and independent perspectives. He argued that an enemy of humanity is the majority, which is made up of ignorant people, who cling to social lies, suggesting that they take a long time to be right, if ever. Other important opinions are: Mark Twain, "Whenever you're on the side of the majority, it's time to pause and reflect." Leon Tolstoy, "What is wrong does not cease to be wrong because the majority participates in it." George Bernard Shaw, "The minority are sometimes right, the majority, on the other hand, are always wrong." Søren Kierkegaard, "The minority is usually made up of those who really have an opinion of their own, while the strength of the majority is illusory and based on blind following." Albert Einstein, "What's right isn't always popular, and what's popular isn't always right." In 2020 there was already an awareness that the impact of industrial revolutions could be negative, and that this is apparently still happening. Digital natives are the first children with a lower IQ than their parents. This originates in the scientific gap that is forming. One aspect that becomes fundamental is the lives of professional people. Although professional development normally evolves to its maximum level at the end of university, however, it is common for professionals to lose knowledge during the exercise of their work and reach low levels of useful scientific knowledge. In the example, after high knowledge developed at the university, the actual exercise is limited to Excel, which is fundamentally arithmetic. This is another barrier that must be overcome. Now GPT is the intelligent, and super-fast, consultation of what is recorded on the internet, which limits many professionals to this knowledge. GPT hallucinations. ChatGPT, what are hallucinations and why are they a problem for AI systems? Is the article written by Bernard Marr that has been taken as a reference. What is hallucination in AI? Hallucination in AI refers to the generation of outputs that may seem plausible but are incorrect or unrelated to the given context. Thus, GPT hallucinates information on which it has not been explicitly trained, leading to unreliable or misleading responses, which arise from biases inherent in the AI model, and/or a lack of understanding of the real world. The biggest problem with a hallucination is not knowing that you are hallucinating. This can be difficult to clarify, so it is necessary to know what it is not to hallucinate. The main formal hallucinations problem are: erosion of trust, ethical concerns, impact on decision-making, and legal implications. There are several ways GPT can be enhanced to reduce hallucinations. Enhanced training data, ensuring that AI systems are trained on diverse, accurate, and contextually relevant datasets helps minimize hallucinations. Red Team, AI developers can simulate scenarios to test the AI system's vulnerability to hallucinations and iteratively improve the model. Transparency and explainability, providing users with information about how the AI model works can help to understand when to trust the system, and when to seek additional verification. Human in the loop, bringing in human reviewers to validate the results of the AI system can mitigate the impact of hallucinations and improve the overall reliability of GPT. As GPT becomes more common, addressing the phenomenon of hallucination is essential. By understanding the causes of hallucinations and investing in research to mitigate their occurrence, the users can help ensure that GPT is used responsibly and effectively. Optex GPT is the current research and development plus innovation project, based on artificial intelligence, focused on generating a new version of the Optex optimization expert system, fundamentally aimed at generating a new interface, for modelers and users, of Optex, based on GPT-type artificial intelligence. Optex GPT in a GPT enterprise application. Following the principles of Generative Pre-trained Transformer AI, Optex GPT will be the advisor that helps mathematical modelers, and professional users, when they require solutions in line with today's cutting-edge technology. Optex is focused on the implementation of artificial brains, conceived as a union of optimization models, with information systems. In the development and maintenance of high-complexity mathematical programming, Optex avoids the intensive use of resources for programming computers. The process of uploading Optex will be a more interactive activity through generative artificial intelligence, such as ChatGPT Omnichannel 4.0. In this way, the user will be able to communicate with the Optex model database, and use all the documents produced by HI for the management of the system. All through a conversation, out loud if you will, with Optex GPT. At the limit, if the user wishes, Optex GPT can perform the entire process in a single step, until the results are delivered. There is no need to store intermediate results. The basis of the Optex GPT conversation will be based on so-called prompting engineering, called by HI as the engineering of ideas. Optex GPT will be a specialized generative artificial intelligence to work in the Optex Optimization Expert System environment, which will be powered by mathematical models that exist in the current Optex database, and of all new models that will be introduced. Technical documentation that supports Optex, and the mathematical models developed, and general technical information. On the other hand, from this knowledge information, Optex GPT will help the user build new mathematical models. Several GPT models will be developed, in order to serve users with different levels of experience. The main product is the management of MES, Mathematical Modeling Information System. From the correct configuration of the MES, the modeler will be able to configure the required algorithms, link them together, and generate the computational code of their choice. Finally, she will be ready to run the multi-problem models. The data source for building a model can be the description of the real model, and/or the algebraic formulation, and/or pre-existing models in the Optex database. The main product is the management of IDIS, Industrial Data Information System. Most of the information is in videos on HI's YouTube channel. This information must be incorporated into Optex GPT. Optex GPT has internal functions to convert a video, or a group of videos, into white papers in Optex format. As an advisor, Optex GPT will have access to a database of documents, some generic and some specific, to facilitate the understanding of the company-wide optimization system by the user group. The image shows the connectivity of the Optex and Optex GPT databases. The Optex GPT database stores different types of documents oriented to the models and solutions that the user handles. Optex Expert System Database, Optex Manuals, User Application Manuals, manuals of the work carried out for the user, and technical documents such as papers and videos. Alfred North Whitehead affirmed, "Civilization advances by extending the number of important operations which we can perform without thinking of them." GPT is a definitive step in this direction. HI considers that today artificial intelligence is generative pre-trained transformers and mathematical programming. Tribute to Hernando Duran Castro, my master's professor, in 1975, at the Universidad de los Andes. Nothing is necessary, nothing is enough, everything is useful. I added, always must learn. May Hernando rest in peace. Thank you very much for your attention.